Hello and welcome to MT3 again, and now we are looking at special types of square matrices. The stuff is in Riley, Hobson and Bence 8.12, and we'll be covering most of this rather long section. So what are the kinds of special square matrices we'll be looking at? Well, the first is a diagonal matrix, which we've already seen before. Then we come across a symmetric and antisymmetric matrix. Orthogonal matrices, of which the rotation matrix is one, and it's a rather important class. Hermitian matrices, very, very important class. Unitary matrices, equally important. And normal matrices. Now this is something which you may not have heard of before, but it's all of these are special examples of a normal matrix. Okay, so let's start with the ones we've seen before. Just to remind you, a diagonal matrix has its non-zero terms only along the diagonal and zeros everywhere else. Now a short form of writing this is that the ijth element of A is equal to aii times the Kronecker delta ij. Just to remind you, this delta ij ensures that we have, when I is not equal to j, that means if you're off the diagonal, then we get a 0, and if I is equal to j, then we get aii. So we have diagonal terms only. Now once again we have shown this, and I'd like to remind you, it's in one of the earlier tutorials, that diagonal matrices of the same dimension commute. That is, if A and B are diagonal matrices of both dimension n by n, then A times B is equal to B times A. Alright, then we have symmetric and antisymmetric matrices. Now these are defined as follows. A matrix A is said to be symmetric if A is equal to A transpose, and it's antisymmetric if A is equal to minus A transpose. Here are two examples. So here's an example of a symmetric matrix, 1, 2, 2, 3. It's equal to its transpose, and this one, on the other hand, because of the minus sign here, flips sign if you transpose it. Okay, now any matrix can be written as the sum of a symmetric and antisymmetric matrix. This is how it's done. If you take a general matrix A, you can always write it as half of A plus A transpose plus half of A minus A transpose. Essentially, we've just added and subtracted half A transpose. If you define the first term to be a matrix P, it's easy to show that P is symmetric, and please show it. And then Q is antisymmetric. Please show this. So any matrix A can be written like this. Now here's a question which actually is solved in Riley, Hobson and Bence. Let's try and solve it here. If A is an n by n antisymmetric matrix, show that the determinant of A is 0 if n is odd. Now before looking at the answer, pause the video here and try and show it yourself. Okay, but here's how the solution goes. Let's see. If A is it's an n by n antisymmetric matrix, right? So therefore we know that A is equal to minus A transpose. Now let's take the determinant of both sides. So we have oh wait, let me write this as is equal to lambda A transpose, where lambda is minus 1. All right. Now take the determinant of both sides. So you have, therefore, the determinant of A is equal to the determinant of lambda A transpose. All right. Now A transpose is another matrix. Let's call it B. So let B is equal to A transpose. So this is equal to the determinant of lambda times B. Now we know from our from the list of properties of a determinant that if B is an n by n matrix, which is what it is, then this is simply lambda to the power of n, the determinant of B. Also from the properties of matrices, so let's write this down back in terms of A. So that's lambda to the power of n, the determinant of A transpose. Now we know from another property of determinants that these properties, by the way, you'll find them listed in Riley, Hobson and Bence on the determinants. Let's see if we can find it quickly. Here we are. Here's 8.51, which is lambda A is equal to lambda to the n times determinant of A. And the other property we are using is the determinant of A transpose is equal to A, which means this itself is equal to lambda to the power of n times A. Alright. Now what is lambda? Lambda is -1. So finally we get -1 to the n times A. Okay, now if n is odd, what this means is the determinant of A is equal to minus the determinant of A. Therefore, either the determinant of A, the determinant of A is 0, right? Nice and simple result there. All right, so let's move on. What's the next thing? It's orthogonal matrices. Now this is an important class of matrices. A matrix is said to be orthogonal if its transpose is equal to its inverse. So A is orthogonal if A transpose is equal to A inverse. This is quite nice because then to get the inverse of the orthogonal matrix, all you need to do is to take its transpose. And I'd like you to check, let's draw a line here. The rotation matrix in 2 dimensions if you go back to when we looked at specific examples of linear operators, we defined the rotation matrix as, if I'm getting the signs right now, so there were cosines on the diagonal, and now I'm not sure I've got the signs right, but you could check it for yourself. It's either minus here or minus there. I can't remember which one it is, but it shouldn't matter. So show that R transpose is equal to R inverse. Yeah, that's a question for you. Now, the determinant of an orthogonal matrix is special. It's equal to plus or minus 1. And here's how it's going to end up. So first of all, if A transpose is equal to A inverse, therefore we must have A inverse A is equal to the identity, and this must be equal to A transpose A. Alright, now how do we show that the determinant of A is equal to plus or minus 1? Well, let's see. Start with the determinant of this equation here. So the determinant of the identity is equal to the determinant of A transpose A. Now the determinant of the identity is just 1. Therefore 1 is equal to the determinant of the product of 2 matrices is the determinant of each matrix, the product of the determinants of each matrix. The determinant of the transpose of a matrix is simply the determinant of the matrix. Now we are using all these results without proof of what the determinant does to matrices. So that's just equal to the determinant squared. Therefore, we get our result. The determinant of A is plus or minus 1. Alright. Now another important property of orthogonal matrices is that they preserve the lengths of real vectors. Orthogonal matrices preserve the lengths of real vectors. That means a rotation, since a rotation matrix is an orthogonal matrix, it doesn't change the length of the vector, it just changes the direction. Okay, we've taken it for granted, but let's show it over here. So what is the length of a vector? It's the norm. The norm of vector x is its length, and that's defined as the square root of x with x. Now, for the purposes of this proof, I prefer not working with the square root of something. I prefer working with the norm squared. So what we're going to use is the norm squared, and we don't have the square root in here. All right. Okay, so let's start. So as a reminder. All right. So let's say we have a rotation matrix A, and it operates on a vector x to give us another vector y. Okay, such that A is orthogonal, therefore A transpose is equal to A inverse, or A transpose A is the identity. Okay, sorry, I used a single line. There we are. Now, let's consider the norm squared of y. That's equal to the inner product of y with itself. These are vectors here. And we know that this can be written as y dagger y. Now, because y is a real vector, so that's the important part here, we can write this as y transpose y, because for a real vector the dagger is the same as a transpose, because the complex conjugation doesn't do anything. Okay, so that then is equal to y is equal to ax transpose ax, and well, I think I can fit it in here. Now remember what we derived some results for the transpose. If you have the transpose of A times B, it's equal to the transpose of B times the transpose of A. So this then is equal to the transpose of x times the transpose of A, and then we have A x, but the transpose of A times A is the identity, so that's equal to x transpose the identity x, and that's equal to x transpose x. I'm really squishing it in here, and that's equal to the norm, the inner product of x with itself. I think I have to go on to the next slide now. Therefore, and of course that is simply the norm squared of x, therefore the norm squared of y is equal to the norm squared of x. Now, since the norm of any vector is greater than or equal to 0, therefore we can take the square root on both sides, and we have only one possible solution, the positive one. We don't have a negative one. So that's why you need this here. Therefore i.e. dest, the lengths of vectors are preserved by an orthogonal matrix. Right. Okay, next on our list then is, what is it? It's Hermitian matrices. Now, Hermitian matrices are really very important, and I think you already know about it in your quantum courses. So I'm going to make it red. A Hermitian matrix A is defined. A is a Hermitian matrix if A is equal to A dagger. And we're going to see that Hermitian matrices have all kinds of wonderful properties that will come in later. For now, just have A is equal to A dagger. And we, like the symmetric and antisymmetric matrices, you have anti-Hermitian matrices possible. A matrix A is said to be anti-Hermitian if, guess it, A is equal to minus A dagger. Alright. So in a way, the concept of hermiticity is the generalization of the concept of a symmetric matrix, because now it applies to both real and complex matrices. It's more powerful in a way. Okay, now like the symmetric antisymmetric matrices, any matrix can be written as a sum of a Hermitian and anti-Hermitian matrix. Can be written as the sum of a Hermitian and anti-Hermitian matrix. How is it done? Exactly the way we did symmetric and antisymmetric. If you have a general matrix A, we can always write it as a half of A plus A dagger plus half of A minus A dagger. And as before, if you define this to be P and this to be Q, then it's easy to see that P is equal to P dagger. That means P is Hermitian, and Q is equal to minus Q dagger. Therefore, Q is anti-Hermitian. All right. So that's that. Next, we come to unitary matrices. Oops, wrong thing. Let's use that. Unitary matrices are the generalization of orthogonal matrices. A matrix A is said to be unitary if A dagger is equal to A inverse. Now, in other words, therefore, A dagger A is equal to the identity matrix. It also means that, let's see, what can be, oh yes, unitary matrices preserve the length of any vector. So Now, orthogonal matrices preserve the length of a real vector. Here, it's generalized to any vector. And the reason is should be quite easy now. We start again and let y is equal to some unitary matrix A times X, where A dagger is equal to A inverse, or A dagger A is the identity. Then consider the norm of y squared. That's equal to the inner product of y with itself. No, I keep forgetting to put the vector bar under my y's. Right, so that's equal to y dagger y, and that's equal to, let's go on to the next line. Y itself is 8 operating on x, so that's a x dagger times a x, and you can see where this is going. It's pretty much the same kind of proof as with the orthogonal matrices case. We swap the order when we bring the dagger in. It's x dagger a dagger a x, and this thing here is the identity matrix. Therefore, this is equal to x dagger x, which is the inner product of x with itself, and that's equal to the norm of x squared. And once again, because the norms are greater than or equal to 0, therefore y, the length of y is equal to the length of x, i.e. lengths are preserved. Right? Now, you will encounter unitary matrices as you will encounter Hermitian matrices in quantum mechanics. It's used extensively there. So more, you will, this is something which you really need to understand carefully, because it's pivotal in the algebra of quantum mechanics. Right. And we'll often talk, when you get to more and more advanced quantum courses, you'll often hear this phrase, a unitary transformation on something leads to something else. So if you're dealing with spins or dealing with rotations in various spaces, this is where it's become quite essential. And the final kind of matrix is a normal matrix. These are the A is said to be a normal matrix if A dagger A is equal to A dagger, i.e. A commutes with its Hermitian conjugate. Okay, now what I'd like you to show, this is your homework. You'll find more on this in Riley, Hobson and Bence. Show that Hermitian and unitary matrices are special cases of normal matrices. Special cases of normal matrices. I should add one more thing. It's Hermitian and anti-Hermitian matrices are special cases of normal matrices. Please show this. All right, so that's our list of of special matrices, and these are all matrices which which physicists have found important in various scenarios. So and they have interesting properties. For example, we will show when we come to eigenvalues that Hermitian matrices have rather special eigenvalues and eigenvectors. There's something quite special about these matrices, and they just have uses in many scenarios. So we'll stop here. Thanks for watching.